All right, so this video is going to be going over these first couple of Newton's law problems that I gave you guys, and this is going to be showing you how to draw free body diagrams and to ultimately set up equations to determine what the acceleration of an object is going to be. Okay, so looking at our problem-solving strategy, what we see is that the first thing we need to do is draw a big diagram. Well, fortunately, here I've done this already, so here we already have step one, and this is to have a big diagram. So the next thing that we want to do is we want to draw a coordinate system for this object, and so that is going to be our step. That is going to be our step 2. So we want to draw a coordinate system, and this is going to allow us to break our forces into components. And so looking here, we're going to have, I'm going to call this the y direction. So this is going to be the plus y direction. And this is going to be the plus x direction. So there's our plus x direction. Okay. So step number 2 is completed. Now, step number 3 is going to be to draw a free body diagram for each object of interest. Now, fortunately for us, there's only this one object, and so some additional notes here for our free body diagrams. We want to make sure that we're including the force of gravity, and we're identifying points of contacts, and for each point of contact, there's going to be at least one force. Okay, so let's go ahead and look at this over here. So we have our block here. We have some force of gravity that is going to be going vertically down. So this is going to be Fg is equal to mg. We have some force that we're applying from the side over here like this. So this is our Fa. We have some normal force, and we have some force of friction. Now we have to be careful with the force of friction because the force of friction is always going to oppose the direction of motion. And so here, what that says is that our force of friction is going to go this way. Okay. Now, I didn't draw these all to scale, but this gives us an idea of what these forces are going to look like. So this is going to be our step 3. So the next thing that we want to do on this is to use our free body diagram. Well, before that even, we want to write down Newton's second law. Okay. So coming back over here, we have our Newton's second law. So this is going to be step 4. So step 4 is going to be write down Newton's second law in general. So this says that the sum of the forces is equal to the mass times the acceleration. Sum of forces in the x direction is equal to max. Sum of forces in the y direction is equal to may. Okay. So after we've written Newton's second law here, what we want to do afterwards is to use the free body diagram to evaluate the Newton's second law equations. Okay, so we have a free body diagram here, but we're kind of missing some core features of the free body diagram, because in order to use our free body diagram, all of our forces need to be broken into components in the directions that we've given for our coordinate system. So in order to do this, what I'm going to do is I'm going to break some of these vectors into components. So here is a y component of gravity per the way that I'm defining gravity, and here is the x component of gravity. Now this angle right here is going to be the angle theta, and so this says that this is going to be Fg times cosine of theta. Okay, and this is going to be Fg times sine of theta. Now we can do the same thing for our applied force, and so when we're looking at our applied force, this is going to say that here is the what we're calling the y component of the applied force, and here is the x component of the applied force. Okay, so now everything's written in terms of components. We're ready to use our free body diagram and our coordinate system to write our equations. Okay, so let's go ahead and do this now. So in the x direction, we're going to have a minus, this is going to be equal to minus the force of friction, because the force of friction is going to go in the minus x direction. We're going to have a minus Fg sine theta. Fg is going to be mg, so this is going to be mg times sine of theta. And then we're going to have a plus. Now this angle right here, this angle right here is going to be theta. So this is going to be plus Fa times, this is going to be a cosine of theta. Okay. For our y equations, this is going to say that this is going to be equal to n. So we have normal force that's going to be pointing in the plus y direction. We have minus Fg cosine of theta, so this is going to be mg times cosine of theta. And then we're also going to have a minus Fa times sine of theta. Okay? So we have step 5 here. So we've written everything in our free body diagrams here, or we've written our equations from our free body diagrams. And so the last thing that we want to do is we want to use our knowns and unknowns and other relevant information, such as the force of friction is equal to mu times n if something's moving, to further reduce our equations. And so when we're looking at this now, what we can do is we can say that here, this is going to be in motion. This says that the force of friction, so this says that the force of friction, F, is going to be equal to mu times n. We also know that our acceleration in the y direction is going to be 0, because look at the way we're defining the y direction, right? So the y direction is going to be perpendicular to this plane. And the object doesn't leave the plane, it doesn't crash through the plane, so that tells us that this is equal to 0. So what that allows us to do from this equation right here, so this is going to be equal to 0. This allows us to solve for the normal force. So here it says that the normal force is going to be equal to mg times cosine of theta plus Fa times sine of theta. Okay, so now we have this equation right here. We have this equation, we have this equation, and we have this equation. And ultimately what we're trying to do here is we're trying to determine what a sub x is going to be. Okay, so let's go ahead and plug our force of friction into this equation up top, plug our normal force into that force of friction, and what we're going to see is that m a sub x is going to be equal to F times A times cosine of theta minus mu times mg times cosine of theta plus Fa times sine of theta times Fa times sine of theta minus mg times cosine of theta. Now we can collect some terms, and I'm going to move this mass over to the other side. And so in the end what we have is that a sub x is going to be equal to 1 over m times Fa times cosine of theta minus mu times sine of theta minus, there's something wrong here. There's something wrong here. This term right here is a sine. So this right here is a sine of theta. So we see that that one actually came from this equation right here. So this is going to be an mg sine of theta, right? So as always, as you're going through this, make sure that you're checking to make sure everything's consistent line to line. So this is going to be minus mg times mu cosine of theta plus sine of theta. And then the last term is, that's everything. That's everything. Okay, because there's 4 terms in the previous line. I've just collected things in terms of Fa and mg. Okay, so last thing we want to do here is we want to look at this, and we can go back all the way to our free body diagram and make sure that everything that I have written here is indeed consistent. And so let's see. Things that are going to cause acceleration in the x direction. So we know that the applied force and this component, the cosine component, is going to be going up the plane, so that looks good. Then that contributes to the force of friction because of the, that's going to contribute to the force of friction because of the component that's opposite of this angle, so that's going to be the sine. It's force of friction is going to oppose the motion, so this is going to be minus, so that looks good. And then from gravity, we're also going to have contributions to the force of friction. That's going to be the mu cosine of theta, and so that's the portion that's going to be in the y direction. And the acceleration down the plane is also going to decrease this acceleration. So every term that we have here looks pretty good. Okay, so let's move on to the next question. All right, so the next question is really kind of a continuation of the last one, because we're still dealing with blocks on inclined planes with friction. But now, instead of just having one block, we have two blocks, and they're going to be tethered together with a string. And so again, I have my step one written here already because I've given you the picture that we're going to be using here. So here's our step one. So step two is to draw some coordinate system for each one of these objects. Okay. So when I'm doing this, what I'd like to do is I'd like to draw actually a different coordinate system for each one of these objects. And so just to be consistent with the colors that I was using here before, we have green is the x direction. So I'm going to say that for our first block, because we want to always define the direction such that they're going to be the directions that something's going to tend to move. That's the way I'm going to define my x direction here. This is the way I'm going to define my y direction for this first block. And for the second block, I'm just going to have a y direction that doesn't move at all in the x direction. And again, I want to define this in such a way that the plus direction is going to be the direction that it's going to move. Okay, next thing we can do is we can draw a free body diagram for each one of these objects. So I'm going to start with the mass m1. So here's our m1. We know that we have gravity acting down, so this is going to be m1g. We have some normal force, so this is going to be n. Then we have a tension going this way, so we have tension. And then because it's going to be tending to slide down the plane, this is going to also have a force of friction. I'm just going to call F for right now. It's going to be this way. And just to put our coordinate system right next to our free body diagram. Here's our plus y direction, and then here is our plus x direction. Okay. So the next thing that we can do, so this is for object 1, we have object 2 as well. This one is going to have the tension going up, and then we're going to have this m2g going down. Okay, so we've got our free body diagrams. We just need to, sorry, this is not part 2, this is part 3. So part 4 is to write down Newton's second law. So I'm going to have two objects here, so I'm going to do m1. So this is sum of forces is going to be equal to ma vector. So this is going to be sum of forces in the x direction is going to be equal to m1 a1x. Then sum of forces in y is going to be equal to m2 a sorry, this is not a2, this is still m1, so this is m1 times a1y. And then for m2, this only has a y direction, so what I'm going to say is this is just going to be the sum of the forces in the y direction is going to be equal to m2 times ay. So this is our step 4. So here's our step 4. Step 5 is to use our free body diagram and our equations and coordinate system to fully write our equations here. And so when we're doing that, let's first take a look at what's happening for the mass m1 in the x direction. And so if I'm looking at this, again, I need to break all my vectors into components so that they are in the directions that I've defined here in my coordinate system. And so this one right here, because this is the angle of theta, this is going to be equal to, this side right here is going to be an m1g times a sine of theta, and then this one right here is going to be an m1g times cosine of theta. Okay, so let's write our forces in the x direction. So the first force that we have, this is going to be equal to m1g times sine of theta. Then this is going to be minus the force of friction minus the tension. In the y direction, I have a normal force. So we have a normal force, and we also have a minus m1g times cosine of theta. Okay. Now we can move on down to our mass m2. For our mass m2, this is going to be equal to t minus m2g. Okay. So now we're at step 5, where we're applying additional conditions to this and then simplifying our equations. And so the first condition that I can apply here is for my sum of forces in the y direction for the mass m1. Same as before, this one is not going to accelerate at all in y, and so this is going to be 0. And so what this is going to say is this is equal to 0, which says that n ultimately is going to be m1g cosine of theta. Okay. So a small note here, and something I have to be careful of. A lot of students will say that the force of friction, the normal force is just equal to the gravitational force, and both of these problems are actually showing you that that's not true in general. Okay. So the next thing that we can do is to say that the force of friction, because this is moving, the force of friction is going to be equal to mu times n. Let's use this and evaluate what our equation in x is going to be. And I'm also going to move these equations down, and I'm going to collect them in a particular way. You'll see why in a second. The final thing that we can say before we do that is that the acceleration a sub 1x is going to be equal to a sub 2y, right? And this comes from the fact that this string has a fixed length. So these are these maintain the same distance along the string. Okay, so using all of that, I'm going to rewrite my equations down here, and this is going to say that m1 times a1x is going to be equal to m1g times sine of theta minus mu times m1g times cosine of theta minus t. Now the second equation that I'm going to have is going to be I lost a 1 here, so this is an m1. This one's an m2 times, and actually I'm just going to define, because there's only one acceleration we're interested in here, I'm just going to define a1x, a2y, both as just a. Okay, so here, that's just going to say that this is going to be a, this is going to be a, this is going to be equal to t minus m2g. Okay, now, like I said, I wrote this like this in a very specific way, and that's ultimately in order to exploit Newton's third law. And so we've kind of hidden Newton's third law in here, because Newton's third law says the force that object 1 acts on object 2 is the same as the force that object 2 acts on object 1 with a negative sign, right? Equal and opposite forces. So this is actually manifesting itself in this equation, because the force that object 1 acts on object 2 and vice versa is actually just the tension. And we see that they're equal because I've written these both as t, and they're opposite because of the sign, the negative sign that I have in the first equation. And so the nice thing about this is that with the way that I have this written, I can just take these equations and I can add them together, because when I do that, my tension is just going to cancel, right? So we don't have tension anymore. Then this is going to be m1 plus m2 times a. This is going to be equal to, let's factor out our m1g, so this is m1g sine of theta minus mu m1, sorry, I already factored that out. So this is minus mu times cosine of theta minus m2g. And then what we see in the end is that our acceleration A is going to be equal to 1 over m1 plus m2 times m1g times sine of theta minus mu times cosine of theta minus m2g. And just as before, we can go term by term here and ask ourselves, are all of these forces that we have in our final equation consistent with our expectations of what's going to be happening to the system? And the answer is that it is, because for what's causing the system to accelerate, it's really the component of gravity, or the component of the gravitational force that's along the inclined plane. And so that's just going to be this m1g times sine of theta. So this m1g times sine of theta. And what's going to be opposing that? What's going to be opposing that, ultimately, is going to be the force of friction along the plane, which is going to be the m1g times mu cos theta, and the gravitational force acting on the mass m2, right? Because ultimately, if we're considering what tension's doing, tension's just kind of connecting these two masses together so they can talk to each other. But the tension force itself is kind of internal to the system. And so if I'm talking about what's happening to the system as a whole, I'm really only interested in what's happening externally to it. And so that, again, is a good check of our intuition, and we're seeing that our answer is consistent with our expectations. Okay, so that's going to be it for this one. I hope you guys enjoy, and take it easy.